My name is Beatriz Mingo. I'm a research fellow here at the University of Manchester, and today I'm going to talk about active corrosion protection methods for light alloys. I'm going to share with you some of the experimental results that I've obtained so far, and I will also mention some of the plans that I've got for the future. So the aim of my project is to develop an environmentally friendly coating technology capable of improving the long-term corrosion and wear performance of light alloys for weight-sensitive applications. The application of coatings is one of the most common strategies used to increase the lifetime of metals, but traditional passive coatings only act as a physical barrier against the environment, and once broken, they no longer provide protection. Smart coatings, on the contrary, are capable of interacting with the environment, responding specifically to specific triggers such as mechanical fracture, pH variations, or changes in temperature. Depending on the incorporated functionalities, different properties can be achieved. For instance, corrosion properties, self-healing, or super hydrophobic properties. This technology has primarily been implemented in organic-based materials. But the problem is that organic coatings can only be applied in mild environments. They cannot withstand the harsh environments that we can find, for instance, in a vehicle's engine, in the landing gear of an airplane, or in the rotor system of a helicopter. So my question here is, can we transfer all these active functionalities obtained up to now in organic-based materials to ceramics that are much more resistant and robust? Inorganic matrices are also more rigid and inert, so the active functionalization might be a bit more challenging. There are different coating technologies used to manufacture ceramic coatings, but for this work we have selected plasma electrolytic oxidation, also known as PEO. This technique is becoming quite popular because it's very versatile, it's environmentally friendly, and it can be used to coat components with complex geometries, such as the ones manufactured by 3D printing. We can improve quite considerably the corrosion and wear response of light alloys with this technology, but the main problem is that they only offer passive protection. That is, once they break, they no longer protect the material underneath, and corrosion will propagate catastrophically throughout the metal. So the specific objective of this work is to achieve the active functionalization of plasma electrolytic oxidation coatings by incorporating corrosion inhibitors encapsulated into pH-sensitive nanocontainers. Why is it interesting to use a pH-based trigger? Well, because corrosion phenomena is intimately related to pH changes. So when magnesium corrodes, there's a local increase of pH as a consequence of the cathodic reaction, and this will trigger the release of the corrosion inhibitors that will act locally at the anodic and cathodic sites, inhibiting corrosion propagation. Therefore, the corrosion inhibitors will remain encapsulated while the coating is intact and will be released to the media when detecting this electrochemical activity. So how can we achieve this objective? The first step is the selection of the correct nanocontainer. And there are different factors that we need to consider when selecting them. They should have a high loading capacity, they should be thermally and chemically stable, and they should be able to interact somehow with the inhibitor, so it can host it, and it should also be capable of release it when required. There are different materials that meet these requirements. They can either have 3D structures, layered structures, or tubular structures, where they will host these corrosion inhibitors. For this work, we've selected hydroxide nanotubes, which are natural clays formed by 2 layers of aluminosilicates arranged in a hollow tubular shape. At neutral pH, the nanotubes are negatively charged in the outside and positively charged in the inner lumen. This means that they can host negatively charged corrosion inhibitors and will remain encapsulated because they will be attracted by electrostatic interactions. When pH increases, just like it happens when magnesium corrodes, there is a change in the charge distribution of the nanotube. So the outside becomes positively charged and the inner lumen becomes negatively charged. And this will force the release of the inhibitors because they will repeat each other. So the second step is the physical encapsulation of the inhibitors into the nanocontainer. we have selected 3 different corrosion inhibitors. 2 of them are inorganic, 2 salts, vanadate and molybdate salts, and 1 organic. These inorganic salts are negatively charged, so that the release trigger will be a pH change. While in the case of the organic corrosion inhibitor, the 8-hydroxyquinoline, this is a neutral molecule, so there won't be any type of electrostatic interaction with the nanotube, so the release will be time-dependent. We loaded the nanotubes via vacuum-induced capillarity, and this is the experimental setup that we use for the loading. So basically, we prepared a suspension of the nanotubes into a saturated solution of the corrosion inhibitors, and we placed it into a desiccator, and we connected to a vacuum pump and it vacuumed. So we remove all the air, and this forced the loading of the nanotubes. To check if the nanotubes were indeed loaded, we characterized them by infrared spectroscopy, and we can see in this spectra here, at the bottom in black, the spectra of the empty nanotubes, at the top, the spectra of the inhibitor, and in the middle, the spectra of the nanotube loaded with corrosion inhibitors, where we can see characteristic peaks of the inhibitors in the spectra, the same with the molybdate. And this evidence that the nanotubes were indeed loaded. And where exactly are these inhibitors within my nanotube? There are 2 different possibilities. They can either be inside this inner lumen or intercalated within these 2 layers of aluminosilicates. So we characterize them by XRD, and this peak here, the 001, corresponds to this interplanar distance. So if the corrosion inhibitors were intercalated within these 2 layers, this interplanar distance would increase, and according to Bragg's equation, we would observe a shift towards lower 2 theta values in the spectra. We didn't observe such shift in case of the inorganic corrosion inhibitors, but in case of the organic one, we observed a very, very slight shift. So this suggests that the inorganic corrosion inhibitors are loaded in the inner lumen, while the organic, we've got a mixture of molecules in the inside of the nanotube and intercalated within the walls. The next step of the process is the synthesis of the coating and the functionalization post-treatment. Here we have 2 possibilities. We can try to do these 2 steps at once in a single step, or we can do them separately in a double-step process. The single-step process is a little bit more challenging, but it's also more time-consuming. And it's not time-consuming, it's faster. So here we have, so in this process, we are going to try to achieve the direct functionalization of the coating while the coating is being synthesized. This is a little bit more risky because the coating growth is assisted by plasma microdischarges. And these microdischarges might destroy the 3D integrity of my nanocontainers. The second option is to synthesize the coating in the first step and functionalize it afterwards in a post-treatment. So we've tried both approaches, and in the single-step process, we studied a commercial magnesium alloy, an IM50 alloy, using a standard electrolyte, a silicate-based electrolyte, and we incorporated some nanocontainers. And we observed, as we feared, that all of the nanocontainers were completely destroyed during the process. So this agglomeration here are melted nanotubes. This means that the temperature within the plasma microdischarges was too high, and it led to the thermal decomposition of my nanotubes. The nature and the intensity of these plasma microdischarges is directly related to the electrical parameters that we use during the coating processing. So we thought, is it possible to optimize the electrical parameters to achieve less intense microdischarges? So we decided to study the influence of frequency on the incorporation of my nanotubes. And we observed that when we increased the frequency, this led to the non-reactive incorporation of my nanotubes. So we observed that at 500 at 1000 Hertz, the incorporation was partially reactive, while at 5000, we could observe some nanotubes with their characteristic tubular structure. So when we increase the frequency, we reduce the pulse times, and it results in a higher population density of microdischarges of less intensity compared to the microdischarges that we observed at low frequency, that they are less amount of microdischarges, but these are more intense. So can we say that these results are successful? Well, we learned that it is indeed possible to optimize the electrical conditions to achieve the non-reactive incorporation. But the total amount of incorporated nanotubes was so low that I don't think they can have a significant influence on the overall corrosion resistance. So that's why we decided to try the second approach, the double-step process. So here we synthesize the plasma electrolytic oxidation coating using a silicate-based electrolyte, and then we carry out the functionalization using a simple immersion pulse treatment. Here we can see the microstructure of our coatings. It presents a porous and craterized morphology. And here we can see in the cross-section that it's composed by a 3-layered structure comprising an inner barrier layer, an intermediate layer with variable porosity, and an outer layer with quite big folds. And it's this porosity that is going to act as reservoirs for my corrosion inhibitors. So this is how my coatings look after the treatment. So we can see that the halosite nanotubes form a thin layer above the coating, sealing the coatings, penetrating through the pores, and we can also see some clusters of nanotubes. The coatings containing vanadate and molybdate inhibitors looked exactly the same as the coating containing empty nanotubes. And here we can see, for instance, a pore that was completely filled with nanotubes. In case of the organic corrosion inhibitor, the morphology was slightly different. We can see some kind of spiderweb morphology that suggests that the inhibitor was released to the coating even before the corrosion experiment started, which actually makes sense because, as I mentioned before, there wasn't any type of electrostatic interaction between my nanotube and my organic inhibitor, so probably it was leached out from the nanotube at the very beginning. So now let's continue with some of the corrosion evaluation results. So here we are representing the total impedance of my coatings at low frequencies as a function of the immersion time for all my materials. So the first two columns correspond to the PO coating and to the PO coating containing empty nanotubes, and they both follow the same trend. We can see that the corrosion resistance decreases during the first 4 hours, and then after 24, corrosion progresses very intensively. So probably the barrier properties of my coating lasted for 4 hours. The incorporation of nanotubes, of empty nanotubes, had some effect on the overall corrosion resistance, but it wasn't. They didn't delay the start of corrosion phenomena after 24 hours. The next set of columns correspond to the coatings containing inhibitors. All of them, and for all the immersion times, the corrosion resistance was considerably higher. In case of the two inorganic inhibitors, vanadate and molybdate, we can see that they follow the same trend. First, the corrosion resistance decreases after 4 hours, reaching a minimum at 24 hours, and then the corrosion resistance increases considerably. So probably it wasn't up to, well, as I mentioned before, these two inorganic corrosion inhibitors will be released from the nanotubes when there is an increase of pH. So probably it wasn't up to 24 hours when the change in pH was significant enough to trigger the release of the inhibitors from the nanotubes. So once they were released, they act at the anodic and cathodic sites, not only hindering corrosion propagation, but also improving the overall corrosion resistance of the coating. In the case of the organic inhibitor, the tendency, the behavior is completely different to the previous one. We can see that the corrosion resistance slightly increases during the first 4 hours, and then it drops to values compared to the inhibitor-free coating. So probably, as I mentioned before, all the inhibitors were completely released to the media at the very beginning of the experiment, and since there wasn't any specific trigger, after 4 hours of immersion, their effect was completely exhausted. So according to bibliography, the vanadates are anodic inhibitors, molybdates are cathodic type of inhibitors, and hydroxyquinoline is a mixed type of inhibitor. And the corrosion inhibition mechanism is probably associated to the mixture of adsorption and precipitation reactions that reaction that result in the formation of complexes that precipitate on top of my anodic and cathodic sites, isolating my substrate from the environment. However, we would need to do further experiments to figure out what's the specific mechanism in these coatings. So to evaluate the self-healing properties of my coatings, we use the technique localized impedance spectroscopy, which allows obtaining impedance maps at different locations. So to assess the self-healing properties, we did an artificial scratch. Here we can see an optical profilometry image of my scratch. The red part corresponds to the coating, and the blue part corresponds to the exposed magnesium substrate. This impedance map here corresponds to the vanadate specimen, and we can see here in the scale bar that red means high corrosion resistance and blue low corrosion resistance. So at the very beginning of the experiment, the corrosion resistance within the defect where the magnesium substrate was exposed was approximately 13 kilo ohm, while the corrosion resistance at the edges of the image was considerably higher, which corresponds to the coating. So at this stage, probably all the corrosion inhibitors were still encapsulated into the nanocontainers. But as time progressed, could you please play the video? As time progressed, the magnesium substrate started corroding, and this triggered an increase of pH as a consequence of the cathodic reaction that led to the release of the corrosion inhibitors. We can see that the corrosion inhibitors acted at the weakest points of the scratch, partially restoring the protective properties. We can also see that the size of the defect was considerably reduced after nearly 35 hours of experiments. In this case, we didn't manage to obtain a full recovery of the coating, and it's probably due to the large size of the scratch. So we decided to assess the self-healing properties using a smaller scratch. In this case, we couldn't even identify the defect at the very beginning of the experiment. So this means that the defect was probably completely self-healed after the first scan. It's worth mentioning that we only observed this self-healing effect on the inorganic inhibitors, which evidences the importance of the encapsulation to obtain a controlled release of these active species. So let's finish with a brief summary. In this work, we successfully incorporated encapsulated 3 different corrosion inhibitors into halloysite nanotubes. We characterized them by infrared spectroscopy and by XRD to figure out the location of the inhibitors within the nanotube. We synthesized the coating and functionalized it. We tried a single-step process, which wasn't very successful, but we did manage to obtain some self-healing properties using a 2-step process. Now, what are my plans for the future? I would like to evaluate the possibility of using all the type of nanocontainers, specifically fibrosilica and layered double hydroxides. I'm especially interested in these 2 nanocontainers because they have quite a big loading capacity. And I'm also interested at evaluating the possibility of using all the type of deposition techniques, specifically the aerosol deposition method, which is a room temperature spraying technique, which I believe has the potential to be used to achieve the single-step functionalization of the coating. So this is the end, and if you have any questions.
Okay, thank you very much, Beatriz. That's fantastic. Any questions for this speaker? No. Oh, yes, okay. Michele first, I think.
Thanks, Bea. Very interesting talk. I noticed that your functionalization treatment is effectively a simple immersion treatment. How do you know that when you put them in the corroding solution, these encapsulated inhibitors, they don't just float away from the surface?
They are quite well adhered, but of course they are physically adhered. That could happen, but I don't think that happens because I did a corrosion test and we could observe this self-healing. We could observe this self-healing behavior, which suggests that they remain sealing the pores. But yes, it could happen.
Thanks.
Hi, Beatriz. Thanks very much. I was also interested in when you add the inhibitor groups afterwards, after you've made the film and you deposit the structures. That, I suppose, means there's a sort of a lifetime to those things because they're all exposed in sort of open porosity. But would it be possible to actually, have another stage where you actually can seal off some of those locations and encapsulate those inhibitors?
Yes, we can apply a further sealing post-treatment that will prevent what Michele was saying before, so that would keep them inside the pores. Yes, that's a possible approach, and in fact, this type of coatings, PO coatings, would act very as a very good primer for organic top coats because they are very rough. So, if we want them to use this technology for a real application, then it would be necessary to apply this type of treatment afterwards. And of course, that would increase the overall corrosion resistance even further.
If it's okay, I've got one follow-up question. In terms of, it being like wear resistant as well, is it the principal protection mechanism you're looking for is when actually the coating is sort of mechanically broken that you want them to activate?
One of the reasons that for which I want to do this type of functionalization on ceramics is that the ceramic matrix will provide this wear resistance, while the smart functionality will provide corrosion protection simultaneously. So I don't really think that the encapsulation of inhibitors will play a fundamental role on the wear response. I think the ceramic matrix will be responsible of the high wear resistance. But I think that this type of nanocontainers, that most of them present layered technologies, layered structures, could even act as lubricating systems, so they could even provide better wear response. But it's in our plans to assess the tribological properties, and maybe I can answer to this question in more detail next year.
Thanks.
Hi, Beatriz. Thank you. That's a fascinating talk. Have you measured the leaching, the rate at which the materials are leaching out of your?
I haven't, but this is some of the experiments that the students are doing right now, because it's very important to assess the release kinetics to be able to compare them with the self-healing properties. I mean, if we know how much inhibitor we've got and the time it takes to be completely released, this will give us loads of information. So we are doing it, but I don't have the results right now.
Okay, thank you. And in terms of the nanotubes, do you have any control over the size of the pores within them?
Right now I use them like they are. So these are natural clays, but there are mechanisms where you can enlarge the lumen of the nanotube. So if you do an acidic treatment, you can possibly enlarge the loading capacity. At this stage, I'm not that worried about the loading capacity, because I can see that the loading capacity is sufficient to have a significant impact on the self-healing properties. But yes, it's a possibility. It's something that has been done, and many people do it quite often.
Great. Okay, thank you very much.
Okay, another online question. Okay. So did you have a question, Douglas? Yeah. Okay. So Douglas at the front, here's a question. Then we have an online question, and then the next chair of the afternoon is a question.
Oh, okay. Yeah. Could we just go back to the bar chart type graph that showed the
Which graph?
change in the 0.1, that one.
Yes.
Yes. So have I got this right, that the value drops but then rises again after something like 24 hours?
Yes.
Is that right? Or
yes.
Between 24 and 48? So you may have covered this, but what was the explanation for that rise in the resistance?
Yes. If you look at all the graphs, you can see that we have two behaviors, the first 4 hours and then after 24. So probably the barrier properties of the coating itself is the one that lasts 4 hours for all the coatings. After 4 hours, the electrolyte penetrates through the coating, reaches the electrolyte, and that's when corrosion starts. In the case of the coatings without inhibitors, corrosion starts and the corrosion resistance drops. In the case of coatings with inhibitors, corrosion starts, magnesium corrodes, and there is an increase of pH as a consequence of the cathodic reaction. So we don't see the increase on the corrosion resistance until magnesium starts corroding. That's when the pH increases and triggers the release of the inhibitors.
Yes, okay. Yeah, thanks.
Okay, so we have an online question now. Question is from Chi Him Lo. Thanks for the nice talk. Just want to ask, will you look at improving the pH control release mechanism, and how would you do that with the HNTs?
Right now, well, one of the reasons why I selected halosite nanotubes is because the pKa of the nanotubes matches that of the pH variations that we would observe in magnesium. So I'm quite happy with how the nanotubes responds with pH. That's why I selected it. We could change the range at which the inhibitors are released if we functionalize it with further functional groups like amines. So this is a possibility, but right now we don't really need it with halosite nanotubes, although it could be necessary with other type of nanocontainers such as fibrous silica to match the pH trigger that we need to that of the capacity to host it inside the nanotube.
Hi Beatriz, thanks for an interesting talk. Your LEIS maps, you didn't show a map of PEO coating that had no containers.
Yes. Well, it's completely destroyed after the very beginning. So you would see a blue mess there. So it's completely destroyed at the very beginning. So okay. we couldn't even identify where the scratch was.
Okay, right.
I can show you the images afterwards, but it's completely destroyed.
I just wondered if there was any attempt by the system, the magnesium system, to oxidize and shut down.
We didn't observe such behavior.
Okay.
It was completely destroyed.
Right, thank you.